Good day. This is Basic Calculus, topic Differentiability and Continuity. So we have learned that the slope of the tangent line m to the curve y equals f of x is evaluated using the limit of the difference quotient as h approaches 0. In calculus, the function that gives the general formula for this slope of f is called the derivative, and the process of finding the derivative of the function is called differentiation. So formally, the derivative of the function f at x is defined as the limit of the difference quotient as h approaches 0, given that this limit exists. Let's have example 1. Let f of x be equal to x squared minus 1. Find f prime of x using the definition. So since here we are asked to find the derivative of f of x equals x squared minus 1 using the definition, then we will start our solutions with the definition of the derivative. So we have here f prime of x is equal to the limit of f of x plus h minus f of x all over h as h approaches 0. Alright, next step, we will evaluate our function in terms of x plus h. So we have here the limit of x plus h squared minus 1 minus the entire function, which is x squared minus 1. Don't forget to place them in a parenthesis. All over h as h approaches 0. Next, let's expand our binomial x plus h squared. So we have here the limit of x plus h squared, that's just equal to x squared plus 2xh plus h squared minus 1. Distribute the negative sign to x squared minus 1, so we have negative x squared minus plus 1 all over h as h approaches 0. At this point, we can now combine like terms. So combining like terms, we can cancel out x squared minus x squared. Also, we have negative 1 plus 1. Alright, so what we have left here is the limit of 2xh plus h squared all over h as h approaches 0. So this time, we cannot directly substitute 0 to h because it will make our expression indeterminate. So what are we going to do is we will factor out our numerator. So factoring 2xh plus h squared, we have the limit of h times 2x plus h over h as h approaches 0. So from here, we can divide out h over h. H over h is just equal to 1. So we can divide them out. What we have left here is the limit of 2x plus h as h approaches 0. So this time, we can now substitute h to our function. So we have here 2x plus h or plus 0. That's just equal to 2x. So our derivative is equal to 2x. The derivative of x squared minus 1 is 2x. So that's how to find the derivative of a function using the definition of the derivative. Next, let's have example 2. Let f of x be equal to x squared minus 1. So if you have noticed, our given here is just the function that we worked on the previous slide. So let's evaluate f prime of 2 and f prime of negative 1. So from the previous slide, we have found out that f prime of x is equal to 2x. Then f prime of 2 is just equal to 2 times 2. So just substitute 2 to x, so we have 4. So f prime of 2 is equal to 4. And now solving for or evaluating f prime of 1, we have 2 times negative 1. So 2 times negative 1, that's equal to negative 2. So f prime of negative 1 is just equal to negative 2. So that's how you evaluate derivative of a function. So let us recall the following definitions of continuity. So for the definition 1, we have there continuity at a number. A function f is continuous at a number c if all of the following conditions are satisfied. First, f of c is defined, or f of c exists. Second, the limit of f of x as x approaches c exists. And third, f of c is just equal to the limit of f of x as x approaches c. So if at least one of these conditions are not satisfied, then the function is said to be discontinuous at c. Okay? Next, let's go to definition 2. This continuity of a function on all real numbers. So a function f is said to be continuous everywhere if f is continuous at every real number. Meaning to say, if we are going to look at the entire function, we can't see a hole, a jump, or a vertical asymptote. Okay? And next, we have the definition 3. A function f is differentiable at the number c if f prime of c is equal to the limit of f of c plus h minus f of c all over h as h approaches 0. Okay, so keep in mind these 3 conditions of continuity. Now let's go to the cases where the derivative does not exist. So the first one, there is no tangent line and thus no derivative at any type of discontinuity. So at the point in which the graph is not continuous, the graph also is not differentiable, or the function is not differentiable. That means continuity is necessary but not a sufficient condition for differentiability. Next, there's no tangent line and thus there's no derivative at a sharp corner or cusp of a function. So in this example that we have here, okay, that's a corner, that's a sharp corner. So meaning to say at that point, the graph is not, or the function is not differentiable. And third one, when a function has a vertical tangent line. So in which a vertical tangent line occurs at a vertical inflection point. So the slope is undefined and thus the derivative fails to exist. So in this example, we can clearly see here a vertical tangent line. So at that point, the function is not differentiable. Okay, let's practice. What value of x is the graph below not differentiable? So looking at the graph, we can clearly see that the graph of the function has a sharp corner. So at x equals 2, we see a sharp corner here. So we'll say at x equals 2, the graph is not differentiable. Which value of x is the graph below not differentiable? So that's still very obvious. In the graph, we encountered a sharp corner at x equals -2. Okay, so at x equals -2, the graph or the function is not differentiable. Next, what value of x is the graph below not differentiable? So we have encountered a jump at x equals 1. So at x equals 1, the graph is discontinuous and thus not differentiable. At x equals 1, the graph is not differentiable. Okay, here the same instruction. Let's find the values of x in which the function is not differentiable. So here we have quite a few points of discontinuity. We have at x equals -8, we have encountered a removable discontinuity. So at x equals -8, the function is not differentiable. Next, we also have at x equals -2. And lastly, we have at x equals 6. Alright. Now remember, not all continuous functions are differentiable at all real numbers. Okay? For example, we have the function f of x equals the absolute value of x. So graphing the function we have here, okay, it's very clear that at x equals 0, we have a sharp corner, meaning to say f of x equals the absolute value of x is not differentiable for all real numbers. Because again, it is not differentiable at x equals 0. Okay, so that's basically the relationship between differentiability and continuity.